the break, I was explaining how should we organize the data from a training point of view, and there was a concept called data has to be organized in IID with the IID property, which stands for identical, independent, sorry, not the data, but distribution. So data should be independent, identically distributed. Okay, I explained the identical meaning through every epoch. If a certain input produces an expected output, that cannot change. It should continue to, produce the same expected output, regardless which order that data was picked, right? Next concept I was explaining was the stochastic gradient descent. So in this algorithm, we pick a sample, and when we pick a sample, we pick it randomly from the set. Okay, so we don't pick in order, because if we pick in order, then it tends to, again, not do as good of a job of learning from the data. So we pick it randomly, right? So then we compute the gradient, update the weights and the biases, and go back. Essentially, there are two loops over here. Okay, one is the outer loop for I equal to number of epochs. Then there's also for j equal to 0 to number of samples, the training samples. Okay, so there are two loops over here. If there are 50,000 training samples, the inner loop will go 50,000 or 60,000, whatever. Outer loop, we decide the number of epochs, like 10 or 20 or 30. So anyway, this is the typical iteration of the data, right? So identical means doesn't matter which iteration. If we picked a particular sample, the expected output should be the same. It cannot change. Okay. What do we mean by identicals? Identically distributed. So actually, sorry, it should be. I didn't write it. Independent, identically distributed. Okay. So anyway. Okay, so what do we mean by identically distributed? Okay, so let me modify this. Let me clean this up a little bit so that it's easier for us to see what we are doing. So let me rewrite this loop very quickly. So it goes like this for I equal to 0 to number of epochs, for j equal to 0 to number of training samples. Okay. Then pick a sample randomly. Okay. And then compute gradients and update weights and biases. And this, as we mentioned, will be according to the gradient descent rule, meaning W equal to W minus alpha gradient with respect to, so something like this, right? And same thing for the bias. Okay, so if we, and every time we come over here, okay, to implement this, one technique will be shuffle the data and then go in sequence. Okay, or as long as you can guarantee you're picking a different sample each time, that's fine too. But easy way to implement it, like I said, shuffle data. And then you can go into a regular loop. That will be the equivalent of that, right? Okay, so if we do it like this, right? Let me have you understand this a little bit better. So suppose our loss function, let's pretend we have a single weight. It's just a one input type of neuron, right? Let's pretend our loss function looks like this. Okay. So obviously this is the optimal weight. Because for this value of the weight, as you can see, the loss is as low as possible, right? But we don't know what is that weight, right? So in stochastic gradient descent, we may start, remember we start the W randomly. So start W randomly, right? So we may have it over here, okay? So if we pick our learning rate over here, let's say learning rate is very, very small. Then what will happen is it will probably go over here and get stuck over here. Okay, on the other hand, if the learning rate is large, it may jump over here, may jump over here, may come over here, may jump over here. So there is an ideal learning rate. Okay, and typically, we start out high and gradually reduce. So for example, we may start out at 0.1, then make it 0.05 after 5 epochs, after another 10 epochs, maybe we make it 0.01. After another 100 or 50 epochs, we may make it 0.05. So we gradually keep lowering it down. Is there an optimal strategy to this? And the answer is almost yes. What is that strategy? I'll gradually introduce that to you. So anyway, so coming back to updating the weights and biases using the learning rate and using the gradient, right? So let's say the gradient is high. Gradient is very high. What does gradient mean over here? Isn't gradient the slope, right? So for example, over here, is the gradient high?
Yes.
So we will change the weight more, as you can see, right? The change will be more. On the other hand, let's say we are somewhere over here in a flat surface. Okay, how is the gradient over here? Very small, right? So the update to the weight will be small. So the idea is over here, make bigger changes, and then gradually make very small changes until we get to the minimum. So that's the goal we are trying to accomplish, right? Okay, so now the question is, how often should we update this? If you take a look at this algorithm that I wrote, suppose we have 50,000 samples, right? Training samples. So what will the inner loop go? 50,000 times? Suppose number of epochs is 100. So my question to you is, how many times is this being updated?
50,000 times.
50,000 times 100, right? So if we update it after every training sample, then the algorithm is called stochastic gradient descent. Okay, so if we update weight W after each training input, okay, the algorithm is called SGD. Okay, but generally, if we take a look at the behavior of this if I plot the loss function as a function of the epoch. So the way SVD works is it will go fluctuate a lot. Okay, so there's a lot of fluctuation going on until the loss gets lower and lower as more epochs go, as we go through more epochs. And again, the reason is because we are updating too often. So why would it further go up over here after it going down, the loss going down? It could be the next training data that we picked as an outlier, meaning is a noisy data. So obviously, if let's say you were given 10 data points, right? 9 of them you know were true. 1 of them you know was noisy data. How would you minimize the effect of the noisy data? What would be a general technique? If you took the average, right?
Yeah.
Okay. So, so same thing over here. Rather than updating, what we do is we write another loop over here. Okay. We say for k equal to 0 to batch size. Okay, and this num training samples obviously will get divided by the batch size. So then what we do is, as we are computing W equal to, we keep adding it. So we do W plus equal to. Remember in Python or C# plus or C, W plus equal to means just W equal to W plus whatever the new value is. Right? So after we have accumulated through the whole batch, so then the weights and biases will be updated, update W based on average gradient of the batch. Say it again.
Dropout. Where we have the result of dropouts.
Okay, this one has nothing to do with the dropout. So this one we are simply talking about how often should we update the weight.
Yeah.
And I was saying if we update it after every training sample, then the loss may go down, then it may go up, especially if there's noisy data. But let's say the batch size is 10, right? And even if one of them is noisy, if we took the average of all the gradients, so we did basically this part over here is sum divided by 10, as in if 10 is the batch size, then we update the weight. You guys get the idea? So then obviously we'll remove the noise, and if we, so this algorithm where we further go through the batch size is called mini batch gradient descent, or mini batch SGD. The mini batch size could be 10, right? Another alternative would be, don't even have the inner loop. Okay, remove the inner loop and sum these over all 50,000. So sum it over the entire 50,000, then take the average of the 50,000, and then update the weights at the end of the inner loop. Obviously, there will be, if we plot the, and that's called a batch SVD. So this is the full batch, like all 50,000 or 60,000. So obviously this will go and give us very slowly the minimum. The only problem is this is very slow. Okay, for it to keep reducing the loss, it will take a long, long time. So computationally very slow. Okay, this is computationally fast. Because every time we'll have to run through very few epochs. Okay, in the third category, if we take a look over here, loss versus the epoch, it will be a little bit noisy, but not too bad until the loss becomes very low. So mini batch is the preferred approach in all of deep learning. Every time we do any training, we'll pick a batch size. Batch size could be, so the batch size over here varies between, like I said, 10 to a few hundred. Typically, it's a power of 2. So typically 32 or 64. For those of you who were in the computer architecture would remember, because ultimately we'll run the algorithm on a computer, so everything is converted to a power of 2. Anyway, so we'll pick a batch size of 32. So once again, the idea is accumulate all the gradients, just the gradients, okay? The partial derivatives, 32 times. Take the average, and then adjust this by dividing the sum by whatever the batch size was. If batch size is 32, you divide this by 32, the sum of these, and then update the weight and update the bias. Okay, so now let's pretend we pick the, or let me make it easier. Suppose we pick the batch size. Okay, suppose we pick batch size, and this is again the mini batch size I'm talking about, equal to 256. Okay, so now I want to explain to you what do we mean by IID, the identically distributed. Okay, so suppose we are doing digits, right? We are doing digit recognition. So, or let me even make it easier to understand. Let me make the batch size 512, even though that's high, but just for the sake of understanding. Okay, so how many classes do we have in digit recognition? 10, right? 0 through 9. So if we randomly picked 512, we have 60,000 training data total. We randomly picked 512 out of that to pick a batch. Okay, what would you expect, roughly speaking, the number of zeros, the number of ones, the number of twos, if there were total 512 images? No, forget 60.
50 of each.
50 of each, roughly speaking.
Equal distributed,
Yeah.
yes.
So that's what we mean by sort of identically distributed, right? Suppose the first batch you picked, okay, there were 50 zeros, 50 ones, and so on. It could be 53, 55, but within roughly speaking. Okay. If the next batch you picked, so this is the first batch you picked as you're going through the loop and training, right? Second batch you picked, suppose there are 300 zeros. Everything else is very like 2 or 3. So that is a violation of the IID concept. Okay, identically distributed means every batch will roughly contain similar distribution of the classes of data, right? Okay, so so when we write this random shuffling and picking the data, we have to keep in target the IID concept. If you wrote the code poorly, and again it's favoring one class or the other, what will happen is your network will do a great job at recognizing zeros, but do a poor job on recognizing some other class, right? So again, for most of the work that we do in the beginning, you'll see it's very easily achieved. IID is very easily achievable. Later on in the last part of the course, we'll go into deep reinforcement learning, where we are teaching the computer to learn something, for example, could be a driving path, or could be playing a video game, or could be a robot trying to pick up something, right? So in deep reinforcement learning, what happens is it's very easy to forget the IID concept and pick a data where whatever we are teaching it will just learn that and not anything else. Okay. So anyway, hopefully, so to summarize, 3 key things that we talked about from the algorithms point of view recently. One was there are 3 variations of the SGD algorithm, or 3 variations of the gradient, stochastic gradient descent algorithm. And what are the 3 variations? Just the regular SGD. Okay, every sample produces a gradient. And update weights perfectly. Okay, what's a mini batch? Compute average of batch of data. Batch average of gradients of batch of data, and then update weights based on this average. Based on the average grade, right? And the last thing was full batch, or often referred to as batch. So this is basically same as the mini batch, but applied to the entire training data. Okay, so here we take average of entire training data. And but when I say average, average of gradient of entire training data before we update the weights. Okay, and which one is the best, considered the best out of all of these? The mini batch. So this is what we'll be following. Okay, so still in the mini batch, like I was explaining, I erased it over here. The next question is, what is the optimal learning rate? So in the next lecture, I'll go over the theory of this and show you what are the techniques. This is still an open, unsolved problem, but there are some heuristics available to us so that and the general idea is we start the learning rate high and gradually we reduce it. Again, why we gradually reduce it? Intuitively, okay. Okay, so as we come over here, we are moving faster. Once we come to the flat part, our gradient is very small, so we want to make small changes to the weights. If we make a high change to the weights, then the possibility is it will jump out of here and move to a non-optimal set of weights which won't produce as good of a loss function, right? Okay, so let me see how much time do I have today. Okay, let me go 10 more minutes, clarify one concept, and give you at least the initial idea, and then next time I can finish the theory of it. Okay, and in your next assignment, by the way, you will be playing with the batch size. You'll be playing with the SGD mini batch. You'll be playing with the number of neurons, just like I showed you, but you'll try on your own to see if it makes perfect sense. Okay. So hopefully tomorrow or maximum by Thursday, I'll give you the next assignment. Okay. Okay, so now let's take a look at the digit recognition. Okay, as we mentioned, if we're using the MNIST data set, right? Each is a 28 by 28 pixel digit. So that means the number of inputs that we will feed to our network will be 784 by 1, right? So then in your current assignment, you are already creating okay, I mentioned something like 100 neurons in the hidden layer. And by the way, you will also put a dropout over here to see if that improves the, and as I mentioned, dropout is very simple. You just add another vector and you multiply by it, right? Okay, how many output neurons do we have in our system? 10 in our digit classification, right? So whatever the weight matrices we come up with, 784 by 100, 100 by 10. So let's pretend you programmed it, it's working fine, right? Okay, so now you are testing it. As you are testing it, my question to you is, suppose the actual output it produces is something like this. On the first line, 0.0, 2.07, 0.31, 0.31, point whatever, 1, 2, and all are pretty low, some low values. So these are the 10 outputs it produced. How would you know what digit is it recognizing?
I mean, theoretically, you should pick the highest probability. Yeah, but we have two.
We have two, right?
Yeah.
So okay, let's pretend you decided the very first one, this is 0, this is 1, this is 2, 2 is the highest, even though 3 is equal, right? So even though the chance of this is becoming, is less, still theoretically it is possible, right? Okay, so what if we wanted to do, especially in the last layer, we wanted to create an output layer such that it will maximize the difference, meaning whichever is the higher one, it will make it even higher. Whichever is not being detected will make it lower, right? So, so let's forget the duplicate. Let's say it was something like this, 0.21, 0.26 or something, right? Okay, so what we want to do is we want to make this 0.26 like 0.8 or something, such that this becomes 0.3. Everything else becomes very low, 0.01, so that clearly we can see this is the expected output, as an example, right? So there's a very special activation function that we use in the last layer to maximize the highest output and minimize the non-highest outputs. And that function is called softmax. So use softmax in last layer to create better function. Between different classes. Okay, and the idea in softmax is extremely easy. So suppose we have 10 outputs, right? Suppose I call them A0, A1, A9. So these are the actual outputs. Okay, or let me call them, see, if you take a look at every neuron, right, there's a sum, and then there's an activation function. Okay, so this is the actual output, and this is we call sum 0, sum 1, and let me make it lowercase s, and lowercase s now. Okay, so the idea is the final outputs that we are producing over here, we want to, if A3 was supposed to be recognized, we want to increase its value, and we want to decrease everybody else. So can we come up with a mathematical function which will automatically do this? And the answer is yes, and that mathematical function is called the softmax function, right? What's the formula for it? Very easy. Okay, so what we'll do is, if you take a look over here, the sum is over here, right? Then, so S1 will also be fed over here. S9 after will also be fed over here. So everybody is getting S0 through S9 in their activation function. And the formula for A of I will be e to the Si divided by e to the S0 plus e to the S1 plus e to the S9. So for example, let's take a look at, this is A0, this is A1, right? If I were to write the formula for A1, what will this be? E to the S1. So whatever sum I produced over here, divided by sum of all. Okay. If I looked at, so I can alternatively represent this, right? This A to the I as you can see, e to the S of I over summation I equal to 0, or I can put j over here so that it's less confusing. J equal to 0 through 9, e of Sj. Everybody agrees? So this is the standard form for the softmax function. And again, what's the idea behind? The idea is very simple. Make that output which is already high. Because once we take to the power e, it will further enhance it, right?
But if it's equal, it will produce the same.
Yeah, it will still produce